from that power saturation point that shows where our delta T setting should be. And over time, you know, all systems show degradation, be it the coil, you know, the water treatment, things like that. And you can actually see if you're pulling graphs like this out of the valve, that's where this came from. It's a graph that can be, data is pulled out of the valve, and then we have an Excel tool available on our website where you can plug the data in and it'll give you graphs similar to this sometimes they won't look quite like this. It all depends on how the system's being run. But if you get a graph like this over time, what you'll see happen as the system degrades, your power saturation point will start moving further back.
Yeah, whole coil curve will shift down.
Right. Yeah. And based on this type of information, customers can decide, okay, we're seeing it shift, we need to do some maintenance before it shifts too much. And by doing that, we're limiting, not eliminating, but limiting the amount of time we're in that waste zone. Some of the benefits of using the energy valve, we're able to deliver the exact flow to the coil, or we can deliver the exact load to the space. Now this is just getting back to what Brian was talking about earlier, as far as delivering based on GPM or based on the BTU requirements. And as it says down here, the control signal is directly controlling either the flow or the energy. So, as we said, you can deliver exact BTU per hour to the space, regardless of fluctuations in the pressures in the system. And it can overcome disruptions in the supply water temperature as well. So a higher delta T leads you to more efficient heat transfer, which is going to mean you're using less water, saving pump energy, and in general, just saving money. These are a couple screenshots that you can get when you plug into the valve. I know it's hard to see, the colors aren't real great here, but this screenshot on the left, that's a live view through what we call web view. If you plug into the valve, dial into the IP address of the valve, this will show you live what's going on. For example, this here is the temperature sensor. Up here showing live flow data. On the right, that's part of the Excel tool that we have on our website. That's where you would, again it's hard to see, but the left button says import data. So once you've downloaded data out of the valve, you can click on, and you save it as a file, you can click on import data, bring that data into this Excel, which of course has a macro built around it to create all the different graphs. And then the right button just says calculate. You can see right here, it's calculating and putting the scatter plot out there. That's showing your power usage. Now, we've seen a lot of different curves showing, you know, the power usage and also showing the delta T curve. You're not always going to get the delta T curve. This is a nice graph. It shows the nice curve of your coil. Not all of them are like that either. You know, some, they're all over the place just because the system isn't running very efficient. Like I said, you can access live or long-term data. Now, when you're downloading this data, we have two formats. We have short-term and long-term. Long-term, we can download up to 13 months worth of data, 2-hour intervals. Short-term is 31 days of data, and I believe it's 30 seconds. Yeah, 30-second intervals. So just as a recap, we've got some simplified control, either controlling GPM or your power to the space. You can save energy using the delta T manager by controlling how low you allow the delta T to go. And you can track your equipment performance, which can help you set a maintenance schedule. Does it really work? This gets to some of the case studies that are in the folders there. The first one we had, and really we worked closely with MIT on creating this product. So it was the Hayden Library, 150,000 square feet, 3 floors. Building was built in 1947. We put the energy valve on 6 air handling units. Before putting the energy valve out there, they had a 6.15 degree delta T.
Which was actually good for that building because originally it had its own chiller plant with a 6-degree design delta T, so it was great. But
Was it?
They took the chilled water plant out and hooked it up to the district energy or campus loop, which had a 12-degree delta T, so it wasn't so great.
Was it a constant flow system or variable flow system with the 6.15?
With the 6.15 originally, it was a constant flow system when it was originally designed, but when they put it on the campus loop, it was on a variable system.
Variable.
So, August 9th to October 9th of 2010, you can see that was their original 6.15 delta T. After the renovation and installation of the energy valves on those 6 air handling units, delta T was up to 12.14 degrees.
So we only replaced one coil because it was broken before we went in. So you can see how oversized the coils were. If we could get the 12-degree delta T out of the coil that was originally designed for 6. That was 50 years old, 40 years old.
And this white paper is included in the folder. It was put together by several different people. Somebody from the University of Colorado, Boulder, one of the people that was involved from MIT, as well as a person from Belimo, corporate over in Europe.
When they did the renovation, they didn't change the airflow on it, on that area. It was just water, just basically slowed it down.
Yeah, yep. And they've done a study on the chill water side of their loop, and if they were to go in and replace a free valve with a PI valve or an energy valve, they're estimating about $1.5 million savings a year. So, you got a big campus, you got a big system, your numbers can really add up quick, and then it really just depends on how your system's been maintained and how well you control it.
On that same estimate though, what's the initial upfront cost to change all of that? Did they ballpark that or not?
I don't know what the,
Yeah.
I don't know if I have that. They're up to, I think they've done 12 buildings now on their campus. But I don't know, let me look and see if I have.
I was kind of curious on the payback and all that.
Right, right.
Yeah, we don't have payback necessarily on this one, but let me look. See if I got some.
Another case study that's in the folder there, University of Miami Hospital. This building had 11 air handling units, 2,600 tons of cooling, over 10,000 GPM was being used at a 5.5 degree delta T. after changing out those 11 air handling units to energy valves, raised the delta T from 5.5 to 10.5, reduced the flow from the 10,000 GPM down to 5,600 GPM. Now this one, they did estimate the savings as 66,000 per year. And, okay, yeah, here's the payback, a 2.9-year payback.
Keep in mind, this is a performance contractor that did this job.
Yep.
So don't try to calculate either the amount of energy valve costs or anything like that. Just, you're talking about $198,000 in 11 valves.
Yeah.
We are not making that kind of money. But that guy's sitting at 80 right now, so.
Yeah. Somebody's got to make money, right? This is another case study that we've done. We don't have it printed up yet. We're still working out details with the company as to whether they want to be involved in a case study. But they are allowing us to show this. And what this is going to show, Brian was talking earlier about being able to set up the valve as a pressure-dependent valve as well. So what we're going to look at here is this line down here. That's showing the valve set up in pressure-dependent mode. So that would be just like if you had a standard two-way characterized ball valve, a globe valve in the system. The middle line is showing flow control. That's a pressure-independent situation. We'll see the numbers in a minute. And then the top is when we're bringing delta T management into the equation. So what we're going to do, we're going to look at requirements at a 60-ton load for each of these different types of control. So with position control, we need 240 GPM to satisfy that 60-ton load. Now, if we went to pressure-independent mode, or if we just used a pressure-independent valve and not the energy valve, we're seeing significant savings there in bringing it down to a requirement of 144 GPM to satisfy that same 60-ton load. Now, if you bring the delta T management into it, we've gotten it down to 96 GPM to satisfy that same load. And that's why we're looking at the 60-ton load across all. We wanted to see, comparing apples to apples, basically. How much flow would be required based on each type of control.
So basically, you're at 40% of your original flow, and you're still getting the same amount of output.
Yep. Any questions about what we've gone over? That's the end of the slide presentation. If Brian, okay, great. Yeah.
Attention to the main lines.
How big of valves do these go up to?
6-inch.
Okay.
713 GPM.
Right.
But you can put a, put them in parallel.
Yeah, it runs from 1/2 inch all the way up to the 6-inch.
Okay, just real quick, Don hit on these. First day back. Okay, so Don talking about these coil curves, and he said that he thought this, the power saturation point on one of them might have been maybe picked a little too early, too low. But what this is really showing you is that this cloud of points, basically each one of these points has an associated delta T with it, so it's the same sample at the same time. But you can see that to produce this same 330,000 BTU, we're going from about 65 GPM down to about 47 GPM. So that's the range that this valve was able to control to this BTU, about 20 GPM difference there from maximum. Same BTU output. You see it down here a little bit better, but this is, and we talked about these curves. I don't see these curves. I see a lot of these curves, and I don't see ones that are this pretty, very, very, ever really. Every once in a while. But this is from MIT. This was, maybe a couple hour sample. We got a really good sample. It's nice to put in our brochures and show everybody. But in reality, every system's going to be different. A VAD system from a constant volume system, they're all going to react and act differently. But this shows you again that there's a huge area that we play in with flows. We can get the same BTU output. Okay, and that's what pressure dependent is. It's a great technology. We've used it for 50 years, 60 years. But if you haven't adopted pressure independent technology, this is the benefit. You reduce your flow, you get the same heat or cooling output. Now back to the point of the power saturation point. Sure, we could go up here, and if the 2 wasn't here, you could see this starts to tail off a little bit at the end. But in reality, from point 1 to point 2, we're going from 320,000 BTU to 325,000 BTUs. Okay? So half a ton, basically, if we're talking cooling. A little bit less than half a ton. But we've also gone from 65 to 55 GPM, so 10 GPM difference. What's the cost? What's the associated savings? We've got 1.6 increase for 5,000 BTUs. We've got an 18% increase in our flow. But if you're familiar with pump affinity laws, you know that the horsepower is going to equal GPM cubed. Okay? So it's 65% increase in pump horsepower. So you start talking about the half gallon or the half GPM that Don talked about earlier. You get 200 valves in the system. Now you've got 100 GPM. You start doing the calculation, and you've got huge numbers. That's where the 1.6 million or whatever at MIT comes up. Okay, and it's going to be different with every system. And then we've got all that stuff. But I just wanted to point these out that we've got these clouds, and these point clouds are really where we're trying to play at right here. This is what we're taking advantage of, is this huge swing and where we can get the amount of heat transfer that we want. That's really all I wanted to show you. There's a lot of good stuff in this one, but this isn't. The one other point is you guys are probably all familiar with balancing valves and how systems are balanced. You get close to a pump, close to your source. You're going to have high pressure. You get further out the system. You got low pressure. That's why we put our pressure sensors out in front of the line, so we guarantee we get our flow out there. With that's a lot of slides. You got to be glad you didn't sit through this one. But so we talk about balancing. Okay, I'm not going to tell you to get rid of balancers because balancers play an important part. But you put a PI valve in. You set that basically these electronic PI valves. We tell this thing its max flow is 100 GPM. It's not going to go over that. Okay, it's going to control from 0 to 100 GPM. And you can go up and you can plug into our valve and you can verify that you're getting that flow. So you don't have to go to every valve, every box, and verify the flow through the valve. Okay? Basically, set up your system, verify the total system flow, and you're good. So these basically, we call this dynamic balancing. It's always balanced. It's not, you open all your valves and then you figure out what the flow is at the farthest coil. That's where you set your set point. Your system forever controls there. Unless you're doing VFD reset, I know there's a bunch of other things we can do control-wise, but the simple fact is that these will always be balanced. They're always going to be balanced.
And if you want to prove to yourself, like Brian was saying, you go up to half a dozen of them or whatever the case may be, plug in, make sure you're getting the flow you're expecting to get at that individual coil.
Well, how about the water balancers? They gotten on board with them and everything so they can validate.
Some have,
It's like
some
anything
have,
else.
some haven't. Just like the engineers. Some have taken to it, some haven't. Yeah.
Because if you want to take full advantage of the balancer's gotta
Yes.
factor into his scope that he has less work to do, so that he can put more into the,
Right,
the
right.
cost of that. I think that's probably a challenge in different
But-
markets.
It is.
Did
And
they
it's,
force
you know,
them
it's,
to verify? Because they're gonna hook up their own gauges no matter what.
Right. Now, yeah, let me just clarify a little bit. So we've been talking a little bit, two different types of pressure independent valves. So I started out talking just pressure independent or PICCV, and that was a mechanical pressure independent. Brian alluded to that a little earlier, whereas what we're talking about here, this is an electronic pressure independent valve, ones that have the flow sensors are electronic. With the mechanical, those ones can be ordered with their own taps. Now, with that said, I have run into balancers that we have a guide that says if you're using this valve, these are the methods you should use to balance. I've run into balancers that have said, well, that's not the way we balance. Well, okay, it may not be, but if our valve's being used, these are the methods. I think we give 5 different methods. You know, we don't say you have to do it this one way. We give 5 different methods that we've talked to Neb and Tab that have said, you know, these are approved methods of balancing. I ran into that on a project, and the end user said, you know, okay, I understand that this isn't the way you normally balance. These are the valves we've used. The manufacturer's giving you a way to balance them. Use one of those ways. But yeah, you know, like we said, different balancers have different takes. When we first brought out our pressure independent valves, we dealt with a balancer near our corporate office over in Connecticut and was asking him, you know, his take on this, you know, because same thing you brought up, we thought that, okay, are the balancers going to be pissed because we're taking away some of their job? And this person didn't feel that way. So we were really taking away the biggest headache that he had, and not where he was making the most money, because he had to spend a lot of time, and he made more money elsewhere. So he felt like it was a benefit to him.
So is he gonna set it up by plugging in with his IP connection? I mean, how's he gonna balance that?
This is going to be ordered to the flow that you want.
Right.
And he can plug into the valve, yes, to find out what flow he's getting.
there's also a tool, it's called a ZTH, it's a little,
Right.